Hello guys, welcome back to Maison African Motives. Still on our revisions for engineering science and for working on the statics part. This is August 2023 exams. We shall just want to focus and see how are we supposed to attempt some typical questions. We were given the first part of the question, define the following. We've got the uniform beam and also the uniformly distributed load. So in this case, we have got two different uniform sections, a uniform beam, which is considered that it has the same mass per unit length all along its length. So we are going to have the same mass along the length up to the end point. Whereas if you're talking about a uniformly distributed load, this is considered for a certain section of the length or for a particular length of the beam that you're given, or it can be taken along the whole length of the beam. So this is a load that is distributed evenly along a certain or whole length of a beam. So these are the differences that we are having between the two. All right, let us consider the second part of our question, where we are given study the beam shown in fig 1 below and answer the questions that follow. So this is the beam that we are given. We are given the cross section of a cantilever in this case, and I talked about this cantilever concept of April 2023 exams. So it's just one and the same that we are given. So they are given to calculate the magnitude of the reaction, which is the reaction at A. We are considering the magnitude of the reaction at A in this case. So when you're dealing with a cantilever, the concept there is just on the forces. The sum of the upward forces must be equal to the sum of the downward forces in this case. All right. So if we have to check, there's a distributed load that is taken between 2 and 3, which is 5 meters of 10 kilonewton per meter. So this is 10 kilonewton per meter. So it's going to be 10 times the distance, which is 2 plus 3, which is 5. So 10 times 5, which is going to be a 50. So you are going to have a 50 kilonewton in this case, all right? So you're going to have a 50 kilonewton. And here we are going to have a 15 kilonewton per meter for 4 meters. So we are going to just have it as a point load of 15 times 4 in this case, which is going to be 60 kilonewton. So in order for us to have the reaction at A, we are going to simply apply the concept of the upward forces being equal to the sum of the downward forces in this case. So you're simply saying the sum of the upward forces must be equal to the sum of the downward forces. That is, the upward forces is the reaction at A, which is equal to the downward force. There's a 30 kilonewton. Then we simplified this 10 times 5, which gave us 50 kilonewton. So we're going to add 50 kilonewton, and we also have a 40. So we are going to add, and also a 60. We are going to add these together. So it's 30 plus 50 plus 40 in this case. All right, so that means we are going to obtain a total of 180. So this is going to give us a total of 180 kilonewton in this case. So this is the reaction that we are having at A, which is 180 kilonewton. Then draw a shear force diagram. From there, we are asked to draw a shear force diagram. Remember, a shear force diagram, we simply have to consider how the forces are being taken in this case, and according to a certain scale that you are going to apply, whether it's going to be decreasing, it's going to be a distributed load, or it's going to be a concentrated load. You have to consider each and every part. So I'm just going to have a sketch here of our, all right, I think all right, the other thing that you can see on our diagram here that was not complete is we are given 2, we are given 3, we are given 3, we are given 4. This distance we are not given. This was just a mistake. It was supposed to be 3 meters, and from the actual question, it was supposed to be 3 meters. We are not given there, but that was supposed to be a 3 meters. Okay, so it was just an error, omission. which occurred on that part. All right, anyways, let us consider our shear force diagram on this side. I'm just gonna need a ruler, and you're gonna consider a scale of your choice, but in this case, I'm not gonna have a proper scale because of where I am presenting here. It's difficult for me to have a proper scale, but this is what you're supposed to have. Gonna need a shear force diagram. All right, so a cantilever, this one is gonna be from the positive and up to 0. So we're not gonna expect to have negative values in this case. So meaning to say, we are going to focus more on the positive side. We're gonna focus more on the positive side, that is more on top, above our line, in this case, that is above. So this is what you're gonna have. So like I'm saying, you are going to consider a certain scale of your choice in this case, that is taking from talking about the forces that you're going to have starting from 0, in this case kilonewton, and so on. So you're going to have a scale of maybe 1 centimeter representing 100 kilonewton or 50 kilonewton, but here I'm just going to mark the important points in this case. All right, so let us see what's going to happen. The first part, we have got a support at A. So a support, it is going up, so it's supposed to be a positive. So it's going up, it's a positive. Just indicate with a vertical line. So we've got a support which is positive 180 at A. So we're gonna have maybe according to your scale, this is where you have 180. So like I said, you're gonna have this according to scale. So maybe according to scale, that's where you have your 180 kilonewton. So here I'm just gonna mark the important points, but you're supposed to gonna have this, maybe it's 100, 200 and so on, or it's a 50, 100. It's gonna be up to you. Just choose a suitable scale of your choice. All right, then if we are to check here, we've got a distributed between A and B. All right, so this here, it was just for calculation of the reaction, so we are not going to consider this. We are going to consider between A and B. All right, between A and B, we've got a distributed load of 10 kilonewton in this case for 2 meters. So we are going to subtract, and a distributed load on the shear force diagram is given as a slanted line like this. We're going to have this as a slanted line. Okay, so we are going to subtract 10 kilonewton times 2 meters. It's affecting, so that's in between A and B. So this is just in between A and B, there is a distributed load. So you're going to subtract this distributed load of 10 kilonewton times 2 meters. That is from 180. Remember, we are at 180. So it was supposed to be 180 minus the product of these two. That is 10 kilonewton times 2. So it's going to be 10 times 2, which is going to be, in this case, 160 kilonewton. So that would be the one that you're going to have. And like I said, a distributed load is going to be a slanted. So we are going to mark at 160, maybe 160 is somewhere here, then you join. So it is going to be a slanted line like this. All right. So we're going to have from this point a slanted line joining to this point. Okay, so that's the condition that you're supposed to have at the end. All right, just a little bit here. So I'm just going to join these 2 points from this point up to this point. All right, so that is at 160 kilonewton. So this is at 160 kilonewton. Okay, let's consider we are now at B. At B, there is a point load at B of 30 kilonewton. So a point load, you subtract it and you draw it as a vertical line going down. So there's a point load of 30 kilonewton. So at 160, we are going to subtract, that is at what? At B. It's going to be 160 minus 30, which is going to be 130 kilonewton in this case. So this is a point load. So it's going to be facing down. So you're going to mark at 130, maybe according to your scale. This is where you have 130. So you're going to join, and that's a vertical line that you're going to have at the end. So you are going to join a vertical line in this case. All right, so let me just try to do this. We join up to this point from this point here, and this is a vertical line that you're going to have. meaning to say we are now at 130. So that's at 130 kilonewton at this point. So it's at 130 kilonewton at this point. All right, that's at B. Then let's consider what's going to happen from B to C. From B to C, there's a distributed load still of 10 kilonewton over the 3 meters. So we're going to subtract the distributed load of 10 kilonewton over 3 meters. So that's between B and C. It's gonna be, we were at 130, so it's gonna be 130 minus the distributed load of 10 kilonewton per meter, which is affecting over the 3 meters. So you're gonna subtract 130 by, which is going to be 100 kilonewton. So meaning to say it's a distributed load, you're gonna present it this way with a slanted line up to 100 kilonewton. So if you mark properly on the graph that you're having and the scale that you're having, it is going to give you exactly, maybe this is where you have your 100, you mark your 100 here after a certain distance. The moment you join, you're gonna see that this will be a slanted line. All right, so we are going to join this with a slanted line, just a little bit like this. All right, so that's what you're gonna have. So we are now at 100 kilonewton in this case. That was the last point at between B and C. And let's see what we got at C. So at C, there's nothing, we just have, that is the end of our uniformly distributed load of 10 kilonewton per watt, of 10 kilonewton per meter. Okay, so the question is that, how are we going to continue from C to D? All right, from C to D, we do not have anything. That's for the 3 meters, these 3 meters. So you're just gonna remain at 100. We are at 100 here. So you're just going to remain at 100. So this one, we just draw a horizontal line for a certain distance. All right, that's for a certain distance. We are just going to maintain at a horizontal line straight from that point, because we do not have any things affecting. We do not have point load. We do not have a distributed load. So it will maintain for a certain distance. We are still at 100. So this is between the point what? This is between the point C and D. All right, then at D, there is a point load at D. So at D, we've got a point load in this case. So at D, there's a point load. So you're gonna subtract. Remember, we are at 100. We subtract that point load that is at D, which is 40 kilonewton. So we're gonna subtract 40 kilonewton in this case. So this will be at 60 kilonewton. So we're going to remain at 60 kilonewton after that. Okay, so that means this, remember, here it's representing, all right, so this is a D. It's 100 minus 60, sorry, which is gonna be okay, so take note where I'm right. 100 minus 40 is supposed to write it here. So it's 100 minus 40, which we got 60 kilonewton, which is at D. So meaning to say, since we are having a point load in this case, we're just gonna join up to 60 going down. So remember, this is 100. So we're just gonna go down, maybe somewhere here. That's where we've got our 60. So we have to join. This is a horizontal line, a vertical line that you're gonna have there. So you're gonna have 90 degrees. We're gonna draw a horizontal line, a vertical line from this point up to 60. All right, so that's the condition here, like this, up to 60. So we are, remember, we are still here at this point, we're still at 100 because it's the same thing as what we had here. So here we're at 100, then we subtract 40. Now we are at 60. So this point here is indicating at 60 kilonewton. All right, then from there, what's going to happen at 60 kilonewton? We are at D in this case. Then from D to E, we do not have anything, just maintain a certain distance of 3 meters. Like I said, it was a mistake. We are not given that distance, but in the actual question, it was supposed to be 3. So there we do not have anything to consider. Just gonna draw a straight a horizontal line in this case. All right, so let us just have a horizontal line in this case. All right, just gonna need something of this nature for the 3 meters that follow. So it's just gonna be something like this. All right, up to this point. Okay, so that's at point E. What's gonna happen now from E to F? Between E and F, there is a distributed load that is affecting here of 15 kilonewton per meter. So we are going to subtract 15 kilonewton per meter times 4 meters. It's affecting for the rest of 4 meters. So remember, we are at 60 kilonewton in this case. So if we subtract 60 minus 15 times 4, this is going to give us a 0. And that's a distributed load, and I said it's going to be like this. That's how we indicate a distributed load on the shear force diagram. So we are going to have this up to 0. So we're just going to have maybe at 0 here. So we're just going to have a slanted line from this point up to 0 like this. All right. So that is the condition of a distributed load. So you're going to join up to 0 in this case. So we have ended at 0 in this case. All right. So remember, this last will be the point before was at 60 kilonewton. So this point here is at 60 kilonewton. This one is at 60 kilo, which is the same as this one on our it's at the same point actually. So you can choose not to write, or you can choose to write it, or just leave it like that. So that is how our diagram was going to look like at the end. So like I said, please use a suitable scale. Then these are the major points that you are going to have on your diagram in this case. So that's how you can end up with a shear force diagram. Then 4.23, it was to calculate the bending moments at the principal points in this case. So you're going to need the bending moments. All right, so like I said, on the bending moments, if you're dealing with the cantilever, you're going to take each point, taking from the right end in this case, from the right side to each point, you're going to talk of A, talk of B, talk of C, talk of D, talk of E, talk of F. We are going to consider these points, all right? And like I said before, remember I said this here, it was a mistake. There's a 3 meters here. I'm forgetting, I'm removing this. Okay, so let us consider having the bending moment at A in this case, all right? Remember the bending moment, simply force times distance, all right? So we're gonna have, that's 4.23. We've got the bending moment at A in this case. So at A, what is it that is going to affect? We have got a distributed load here. So we're going to have a distributed load, which is taken back to A. All right. So this distributed load is going to be affecting between 15 kilonewton between these 4 meters. So it's 15 times 4, which is going to be 60 in this case. It's affecting on these 4 meters. So it's going to be 15 times 4, which is that 60 kilonewton in this case. Then the distance that you're going to take from this point here back to A, this is the distance that you're going to take back to A. So remember here there's 2, 3, which is 5, 8, plus 3, which is 11. Then in between here there is a 2, because we've got 4 meters. So you're going to have 2 meters, 2 meters. So that means we've got a 2 meter there. So that will be this case, all right? So that is say 2, 5, 8, that is plus 10, which is going to be a total of 13, all right, plus this 3, which is going to be a 13. So we're going to have a total of 13 from this point. So it's 60, which is a negative because it's facing down. So you're going to take this as 60 times 13 from this point up to A. We're going to have a distance of 13. So that's a negative 60 times 13, force times distance. All right, then we move on. Going this direction, we are now at 40. So 40 back to A here. It's going to be 3 plus 3, which is 6, plus 2, which is 8. So that's 40 times 8, which is a negative because it's a point load. So it's going to be negative 40 times 8. Then we consider, take note here, there are two things that we are supposed to consider here. Because we are given the 30 kilonewton that is affecting these two. It is separating two things now, B and C, and also between B and A. So we're going to consider between B and C, there's a distributed load because there's a force here. So we're going to consider our distributed load between B and C, between these 2 points, B and C. What is going to be the force that is going to affect? So it's 10 kilonewton over 3 meters, which is going to be 10 times 3, which is 30 kilonewton over the distance back to A. So the distance back to A here is going to be, remember, if we take the distributed load from B to C, it is going to be 3 meters. So 3 divided by 2, which is going to be 1,5 and 1,5. So the distance from this 30 back to A is going to be 3,5. That is 2 plus 1,5, which is 3,5. So you're going to have 30 times 3,5 in this case, and it's a negative. So it's going to be negative 30 times 3,5. All right. That is between the point B and C. Then at B, back to A is 30 kilonewton. Then there's a 2 meters there. So it's negative 30 times 2. All right, negative 30 times 2 in this case. Then if we check between A and B, we are going to consider our distributed load again between A and B. So between these 2 points, A and B, there's a distributed load there of 10 kilonewton over 2 meters. So it's going to be 10 times 2, which is 10. So we are going to consider this as 10 times 2, which is 20. So we're going to consider this as 20 kilonewton taken over 1 meter from the A, because here we've got 2 meters. So 2 divided by 2, that's 1 and 1. So you're going to have 1 meter back to A. So that's 20 times 1 in this case. All right. So this is going to be negative 20 times 1. Okay. So that is how we're supposed to have the bending moment at A, because of the distributed load, and there's a point load at the same time. So you're supposed to consider each stage by stage. You're supposed to consider each stage by stage. All right. So this was going to give us a negative 1285. So that's 1285 kilonewton meter in this case. So that's the bending moment at A. Then we move on to the bending moment at B. All right, so we've got our bending moment at B in this case. All right, so considering B, like I said, from the right side back to B. So this is where we have our B here. So you're going to consider from the right side back to B. All right, I need this one like this. So you're going to consider from the right side back to B here. So there's 60, the one that we talked about before. Then the distance this time back to B here is going to be 2 plus 3, which is 5, plus 3 here, which is 8, and plus 3, which is 11. So the distance is going to be 11 from 60 here back to B. So that's 5, 8, 11. So that's negative 60 times 11. All right, so we're going to have negative 60 times 11, force times distance. Then we move on 40 back to B. So the 40 here, we are going to refer it back to B. So the distance here is 3 and 3, which is 6. So that's negative 40 times 6. So it's going to be negative 40 times 6. All right, we move on back to B again. This is where we have our B here, and that is where we have our 30. But before that, there is a distributed load that is affecting of 10 kilonewton over these 3 meters. So we are going to have this as 10 times 3, which is 30. So you're going to have 30 kilonewton from the distributed load over the distance of 3 meters. So if you divide by 2, this will be 1,5. This will be 1,5. So the distance back to B here is 30 times 1,5. So there's a distance there of 1,5 meters. So it's going to be negative 30 times 1,5. All right. So that's a negative 30 times 1,5, 4 times distance. So that was going to give us negative 945, which is in kilonewton meter. That's the bending moment at B. Then we calculate the bending moment at C, again from the right side up to the point C. So you're going to consider up to the point C this time. So this is where we have our point C from the end. So it's 60 back to C here. If you have to consider at point C, the distance is 2 plus 3, which is 5, plus 3, which is 8. So that's negative 60 times 8. All right, so you're going to have negative 60 times 8. All right, then after that, we've got a point load of 40. So this D back to C, there's a distance there of 3 meters. So it's 40 times 3. So it's going to be negative 40 times 3. 4 times distance, negative 40 times 3. All right, so that was going to give us negative 600 kilonewton meter. All right, then we move on to the bending moment at D. You consider at D, in this case, this is where we have our point D here. So what we're going to consider is only one thing, which is the 60 back to D here. The distance back to D is 2 plus 3, which is 5. So that's negative 60 times 5 in this case. All right, so that's the only part that we have. So it's going to be negative 60 times 5, which is negative 300 in this case. All right, kilonewton meter. Then the last one, in fact, not the last one, because we've got 2 points that are remaining. We've got the point E and the point F. All right, so we've got the bending moment at E. All right, so we've got the bending moment at E in this case. All right, so what are you going to consider at E? We are still considering the 60 kilonewton in this case, but now back to E here, the distance is 2 meters. So it's going to be negative 60 back to E, which is 2 meters. All right, so that's negative 60 times 2. All right, so there is going to be negative 60 times 2, which will be negative 120 kilonewton meter. Then the last part is the bending moment at F. So you're going to have the bending moment at F. At F, there is nothing that you're going to, here, this is the point F. So the distance from the right side here, we do not have a distance. So it's going to be 4 times distance, which is the distance is 0. So it's going to give us a 0 in this case. So the bending moment at F is going to be 0 kilonewton meter. All right, so that's it. That's how we're supposed to answer these questions. All right, you've got a lot. The bending moment at A, at B, at C, at each and every point on your diagram must have the corresponding bending moment. So taken from the right side of your beam, if you are dealing with a cantilever like that, that's the idea. So make sure that you also watch the video on the membership by joining the membership that I talked about more on this cantilever concept, so that you'll be able to understand. All right, so anyways, 4.3, we are now given find the centroid of the shape. So this is an isosceles triangle whereby these two sides are equal, and we're gonna need the perpendicular height in this case. Remember, for a triangle, the y value of our centroid in this case is taken as the height over 3. So we are going to need this height, and we're gonna have this as height over 3 on our centroid. So how are we going to find the height? It's an isosceles triangle. So this will be at 90 degrees, and it bisects this side into 2 equal parts. So if this is 100, divide by 2, this will be 50 millimeters here. This will be 50 millimeters on this side. So meaning you can use Pythagoras to find the third side, because we are given 2 sides on a right angle triangle. So it's going to be h squared is equal to a squared plus b squared, where h is the hypotenuse. 80 squared is equal to the h squared, which is the h of the perpendicular height, not of the hypotenuse, guys. All right, do not confuse there. Plus this b, which is the other side, which is 50 squared. So transpose 50 squared to the other side, it becomes a negative. So that's negative 50 squared is equal to h squared. So that means find h, you're going to have the square root. So h will be the square root of this, which is going to give us 10 square root of 39. Or we're going to have this as 62,4499, which is going to be 45 in this case. So it's going to be 45 in millimeters, all right? So knowing that the centroid, if you are to consider the centroid is going to be the x value over the y value, if you're just given a single shape like that, actually it's supposed to be the value of y in this case, which is h. So we're going to have the x value at 0 and the y value as h over 3. So you're going to have this as h over 3. So that's a 0 here, and h, which is the height, we divide this by 3. We are going to obtain 20,817. So that will be 20,817. All right, 817 in this case. All right. So that was our centroid. 3 marks for that. So it can be just a direct question like that, where you just need to apply the concept of or knowing the centroid of each and every shape. Talk of a rectangle, a square, any shape that you are given, you are supposed to know its centroid. Okay, guys, just revise as you prepare for the exams that are ahead of time.